Okay, this is the fourth question we're going to do in the shear stress theory for beams, trying to find it. We're going to be doing question 1413 on page 329 in the textbook. A W14 by 30 supports the load shown. Calculate the maximum shear stress using the general shear formula in A and then the average web shear approach B. Be sure to include the weight of the beam. So basically, if you recall, the 14 by 30, that implies, or specifically says that the beam weighs 30 pounds per foot. So we're going to add that 30 pounds per foot to the UDL, that's 1,000 pounds per foot. And we'll up that to 1,030 pounds per foot. And that's going to span 19 feet. And that 19 feet times 1,030 is 19,570 pounds, acting as a concentrated load right in the middle. And we need that solely to solve for the reactions of the beam. The problem's quite long, and I wanted to show you here on the paper first, and then we'll put this aside, and we'll get to the solution. So, page one, basically what I just told you, 30 pounds per foot. We're going to combine that, and that's how we get that concentrated load. And obviously, it acts mid-span in the beam at 9.5 feet. I do that for the reactions. If you just go down to this part, it was found that the reaction at B was 59.12 kips going straight up, and the reaction at A was 0.45 kips going straight up. This one's precariously close to zero. If that gets to zero or negative, that basically is going to mean that that overhang is like a lever, is going to make that beam lift up. But because there's 450 pounds still pushing up on it, it's not going to do that. So anyway, from that, notice in this problem they don't give you the maximum shear value, so that implies, they're not going to tell you it, that you have to do the shear diagram, at least the shear diagram. I did the moment diagram as well because I also want to show you the bending stress values at the end of this and compare them to the shear stress values that we're going to compute. So I did both. Anyway, everything I did here in the solution, which I'm going to email you obviously, is found on page 2. So from here on up, this whole section is how I get these values. I'm not going to go through that. To date, we've done, I think, 18 shear moment diagrams, and this is nothing that you haven't seen before. The beam is W14 by 30, and you can look in Appendix A on page 487, and you can see all the dimensions that I pull off of there to do the problem. The area, the depth of the beam, the width of the flange, the width of the web, the width of the flange, the thickness of the flange, and then the moment of inertia with respect to the horizontal axis. Okay, so we're going to use all that. Part A, the general shear formula, basically says tau is VQ over IT. V, we're going to pick off the diagram, which, by the way, we find that V max occurs at point B, and it's 43.09 kips, or 43,090 pounds, okay? And we're going to use that. Q we have to calculate, that's the hardest part. I is looked up in the table, and T is the thickness of the web, and that thickness of the web was given to us as TW as 0.270. So basically, the question asks for the maximum shear stress in the beam, and that's, you have to know that that's at the centroidal axis. So this is cutting the beam in half. What's away from the centroid is two component areas. I call the top flange 1. I call that little piece in the middle 2. Q is equal to AP times Y bar, and when you have a composite shape, A1 times Y1 plus A2 times Y bar 2. So A1, the area of A1 is 0.673 times the thickness, 0.385. Y bar 1 is the dimension from the centroid of that one shape to the overall centroidal axis. That comes out to be this. Okay, the depth here, we know that the total depth, as we found in the chart, was 13.8 inches. That means that half of that is 6.90, so this 6.90 minus half that thickness gives us Y1. Okay, we're going to add A2. A2 is the width there, which is the flange width, which is the web width, which was 0.270, and then the height here we know that this whole height was 0.690, right? This height minus the thickness of that flange gives us that. Together we get A2. And now Y2 is a dimension from the centroid of area 2 to the centroidal axis, right? It's basically going to be the 6.90 minus the web thickness, right? Gets you right there, and then divide that by 2, and we get that expression. Work it all out, you get a Q value of 23.11 inches cubed. We can get to page 3 of the solution, and you'll see that plugging all that in, using all the values from the shear diagram, the computed Q, and these are looked up in the appendix, we get a shear value of 12,674 psi. That's great. Using the average web shear approach, which is a little more straightforward, just using that expression there. Same thing, we're going to take that off the shear diagram, and these two things we're going to look up. Plugging all that in, we get a value 11,567 psi, which, if you do the math, it's 91.3% of the value obtained by the general shear theory, which is more involved, right? So that's what they say. If you have a symmetrical beam about the centroidal axis, you can use that and get pretty darn close. I'd say that's pretty close. Okay, and I just wanted to show you, for scale purposes, 12,600 psi on shear. I took the maximum bending moment, which also occurs at B, 124.64 kip feet. And I want to calculate bending stress there, so I'm going to break that out into inches. I need to make this inches because everything's inches. And the depth of the beam is the value C divided by 2, right? 13.8 divided by 2, that's D is the top number, and then C is 1/2 of D, and then I's from the table. For bending stress, we get a value of 35,000 and change PSI, so roughly 3 times the size and magnitude of bending stress to shear stress. I think that's what you're always going to find typically the case in steel structural beams, and just wanted to point that out. So in a way, this problem really encompasses the whole course. So if you recall, the first things we did was we talked about vectors and what they are, and Newton's first law, and how to take moments and some forces, and we figured out how to do that. And then once we figured that out, we figured out how to take reactions. And then once we got good at reactions, we started messing around with shapes and cross sections and figured out how to get centroids and moments of inertia. This problem made you look it up. It would be better if the problem would have been perfect, in a sense, if we were given a shape of the beam and had to look all that up ourselves. But that's okay. And then from there, we went and used all those techniques and got into shear moment diagrams. And then from shear moment diagrams, we're able to pluck all that and calculate bending stresses and now shear stresses. So this one problem is a good history of the entire class. And if you've gotten this far and can understand it, that's pretty darn good. So any questions, like I said, contact me. I'll be happy to help walk you through it. This is the last example we're going to do for the course, and the homework for the shear stress and beams will be sent out next week. I think there's like 4 problems or something like that. So anyway, signing off. I'll talk to you later.